Hello, this is Tom Meeks, and this is 3D Design for Fun and Life, featuring Moment of Inspiration using the uniquely easy noun and verb method.
This session is project number 4, creating PVC pipe mounts.
There are very few products on the market that are as versatile and useful as PVC pipe. Over the years, we have used them to create photographic product shooting tables, 3D capture stands, photographic lighting hangers and stands, and even a hanging rod for the green screen background I use for Zoom teaching lessons. In this project, we will demonstrate several ways to create basic wall mounting brackets for PVC pipes used to hang backgrounds or lighting. In future lessons, we plan to demonstrate creating additional types of mounting brackets, connectors, and clips for various purposes. For this project, we have created and included a sample file called pvcpipemounts.3dm. It includes 5 3D designs to represent commonly available Schedule 40 PVC pipe sizes in exact inner and outer dimensions to be used to aid in creating mounts for each of the sizes. We will use these examples to demonstrate 2 different design methods to reach the exact same outcome. Here are our 3D pipe samples. 1/2 inch pipe, 3/4 inch pipe, 1 inch, 1 1/4 inch, and 1 1/2 inch. But before we begin designing, let's take a look at a short demonstration that explains how the way a consumer FDM extrusion printer works will affect the techniques and dimensions we will use as we create our mounts.
When we are designing 3D objects to be printed on a 3D printer, taking the type of printer into consideration is very important. We are assuming that the most common type of printer that will be used with the projects in this course is the FDM printer that extrudes plastic through a 0.4 mm nozzle. This type of printer has some characteristics that call for making design decisions. This is particularly true when we are designing 3D printed parts that are to be mated with manufactured items of specific sizes. There is a difference between the specifications we use when designing in any 3D design application and the final printed size we can expect from the average consumer printer.
In this diagram, the cyan cylinder represents a real-world object. The green represents printed plastic, and the red line represents the position of the center of the printer's nozzle. The top circle represents the nominal width of a line being extruded from a 0.4 mm nozzle in midair. The other green objects represent layers created during the print process. What we have tried to do is to calculate the actual width of a printed line of filament based on the height of the print head. If we click Calculate, the area of the nominal round flow of filament we get is 0.1257 millimeters squared. The question we try to answer is when we force the layers into a height of 0.2 millimeters. How wide would the layer have to be to give us the same area? The answer is 0.69 millimeters wide.
The first layer of every print is pressed down even more aggressively so that the part will stick to the printer bed. If it is compressed to 0.1 millimeters high, it should expand outwardly to about 1.1 millimeters to keep the same relative area.
What this means is that the fit between the real-world object and the printed part is different between the center of the design target, nozzle center, and the actual layers. At the very least, we need to offset the design center 0.2 millimeters to adjust for the 0.4 millimeters nozzle width. But since the layers are compressed, we need to make an even bigger adjustment of between 0.3 and 0.35 to account for normal layer expansion.
But that doesn't account for the greater expansion of the first layer, which could be more than 0.5 millimeters. But if we adjust for the first layer, the subsequent layers may not be fitted tightly enough.
The solution to the first layer problem is to chamfer the inside and outside walls of the object so that the spread of the first few layers does not expand beyond the subsequent layer walls. If we chamfer, the only offset we need to consider is adjusting for normal layer expansion, depending on the temperature and printer. And that is usually between 0.3 and 0.4 millimeters.
Using the half-inch pipe sample as our guide, we will use the first of our methods to create a mount. The most important first step is to create a center circle that is exactly the same dimension as our pipe. We show our half-inch pipe, select the bottom view, click on Draw Curve to open Tab 1 of Palette 1, and then click on the Circle Group button. The choices within the group pop up and we'll select Center Circle. The prompt says Pick Center Point, and we'll select the origin as our center point. The prompt changes to Pick Radius, and we'll use the outside edge of the pipe to complete the circle. Switching to the top view, we can hide the sample pipe. The reference circle that remains is the exact diameter of the pipe. Using the offset verb, we'll use this reference to create a circle that represents the inner wall of our mount. Based on the information in our 3D printer explanation, we want to offset the inner wall of our mount 0.4 millimeters. We click on the Construct tab and the Offset Verb Group button. Selecting the Offset Verb button, the prompt reads, Pick Offset Side. We will enter a value of 0.4 in the distance field, move our mouse to the outside of the reference circle, and press the left mouse button. We can now delete the reference circle. The circle that remains will help form the inner wall of the mount, so we need to create a circle to form the outer wall. We'll use offset again with a value of 3 to create a cylinder having 3 millimeter walls. We click on the Construct tab and the Offset Verb button. Because we did not first pick an object, selecting the Offset Verb button, the prompt reads, Select Objects to Offset. Selecting the circle and clicking on Done changes the prompt to Pick Offset Side. We will enter a value of 3 in the distance field, move our mouse to the outside of the reference circle, and press the left mouse button. Select both circles and name them 101 Mount Wall Frames, 20 millimeters. We will use offset one more time to define the size of the mounting flange. We'll select the outer circle and click on the Offset Verb button. Enter a value of 15 and click on the left mouse button to finish. Name this new circle 102 Flange Frame 5 millimeters. We will now extrude our mount wall and the flange. Using the Object Browser, select Object 101 Mount Wall Frames 20 millimeter. Click on the Extrude button. The prompt reads, Pick Extrusion Point. We'll simply enter 20 in the distance value field. We'll next select the inner circle, N102 flange, and click on Extrude. Enter a value of 5. Click on each solid and then click on the Boolean Group button and then click on Union to create a single object. Name this new object 100 1/2 inch mount. The next step is to apply fillet and chamfer to obtain a more finished look. Select the 3D view. Click twice on the outer edge of the flange top to select it. Click on the Fillet Group button and select the fillet verb. The prompt reads, Pick Fillet Radius. Enter a value of 2 millimeters. Click on Done to complete. Rotate and zoom to gain better access to the top of the cylinder. Click twice on the top face and select it. Click on the fillet verb and enter a value of 1.5 millimeter. If you have any trouble, if it doesn't work, you can use a value of 1.45. Click on Done to complete. We will strengthen the connection between the flange and the wall using chamfer. Click twice on the edge where the wall and flange meet. Then select chamfer. The prompt reads, Pick chamfer distances, and we'll enter a value of 2 millimeters and click on Done. Before we chamfer the bottom face, we'll add holes for the mounting screws. Click on the top view. Click on Draw Curve, then the Circle Group button and select Center Circle. Before selecting the center point, we will create a construction line by holding down the left mouse as we move from the edge of the chamfer to the edge of the fillet on the top face. We can then use this line to find the midpoint. Using a diameter of 5, we create our hole cutter. Name the circle 103 hole cutter. We will now use Transform Array Circular to create 4 evenly spaced cutters. We select the origin as our center point for the array and enter an item count of 4. Because we named our hole cutter before we arrayed it, we can select all of the hole cutters using the object browser. Select 100 half-inch mount. Click on Boolean, then Diff. Then use the object browser to select 103 hole cutter and select Done. Click twice on one of the edges of the holes. Then select the edges of all the holes. To create the countersink for the screws, click on the fillet group, chamfer verb, and enter a value of 2. We now need to chamfer both the inside and outside of the bottom face. Select the 3D view and rotate to allow the selection of the bottom face, and click on the face twice to select it. Click on Chamfer and enter a value of 1, and click on Done. The chamfer on the inside ensures that the bottom layer spread of the filament will not reduce the size of the openings for the pipes or the screws, and the chamfer on the outside will help when removing the printed piece. Show the half-inch pipe and see how it fits. This completes the first method we will demonstrate to create a flange. Now we will demonstrate another method that is even more easily scalable. Before moving to the next method of creating a PVC pipe mount, let's copy 100 half-inch mount and name the copy 90_150 half-inch mount profile. Hide 100 and select 90-150. Go to the top view. Click on Draw Curve, select the Rect group, and then click on Corner Rectangle. Starting on the left side of the x-axis, sweep down to include the bottom half of 90_150. Click on the mount, then click on Construct. Then click on the Boolean Group button, and then click on Diff Verb button. The prompt says, select objects to subtract. Select the rectangle and click on Done. Delete the rectangle and select the front view. We'll change the style of 90_150 to cyan. Select the 3D view. Rotate 90-150 until the flat surfaces are evident on the right side. Click twice on one of the right side faces, and then click again on the second face on the other side of the screw hole. Change the style of these faces to magenta. Select the front view. We will use the profiles of these magenta faces to create a revolved profile curve that we can revolve to create a new PVC mount. This will require creating 2 rectangles and then resizing and shaping them. Make sure that Object Snap is turned on. We'll first tackle creating the rectangle that will form the sleeve of the PVC mount. To create the first rectangle, click on Draw Curve, then click on the Rect Group button and click on 3 Points Verb. The prompt reads, Pick Base Point. Our base point will be on the right side of the sleeve just below the fillet. The point will show the end snap. The prompt changes to pick width point. Move directly across to the other side, looking for the end perp snap message. Click to finalize the width. The method changes to pick height point. Move all the way down to the base of the mount and click to finalize. Let's resize the height of the rectangle using the rectangle's points. Select the rectangle. Click on the Edit tab of Palette 2. Then click on the Show Points verb. Align works with individual points as well as objects. Click in an empty area of the screen to deselect everything. Then select just the top 2 points. Make sure the rectangle itself is not selected. Click on the Transform tab of Palette 3 and then the Align Verb button. Select Horizontal Center or Top Align and move the points up to the top of the mount profile and left-click to set. Click in an empty area of the screen to deselect everything. Turn off Show Points. We will now create the second rectangle that will form the flange of the mount. Click on Draw Curve, the Rect Group button, and the 3 Points Verb button. The base point will be the bottom left of the first rectangle. The width point will be the rightmost point of the bottom edge, and the height point will be the top edge of the flange. We need to widen this rectangle. Again, we will use the rectangle's points to do so. Select the second rectangle, click on Edit Show Points. Click in an empty area of the screen to deselect everything. Select just the 2 rightmost points of the rectangle. Click on Transform, Align, and select the Vert Center Align button. Move the right side of the rectangle to the rightmost side of the flange. We will now union these rectangles to form a single object. Select both rectangles and click on the Construct tab, the Boolean group, and the Union Verb button.
Notice that when we union the 2 rectangles, that some corner points remain within the straight lines. These corner points are no longer needed. These were leftover artifacts from the 2 original rectangles' corner points. We will delete them. Turn off Show Points.
Select the new single curved noun object and name it 90_600 Mount Master Revolve Frames. We will now shape some of the corners of 90_600. We'll begin by using chamfer on the corner where the sleeve and the flange meet. If the Construct tab is not open, click on Construct to open it. Click on the Fillet group and select the Chamfer Verb option. Select the corner point where the sleeve and flange meet. Click on Done and enter a value of 2 and click on Done to finalize the chamfer. Now we will apply the fillet verb to the top right corner of the flange. Select 90_600 and click on the Fillet Verb button. Click on the corner point for the top right corner of the flange and click on Done. Enter a value of 2 and click on Done. 90_600 is now complete. You may wonder why we do not fillet the top of the sleeve or chamfer the bottom corners. The reasons for not doing so will be explained as we use this master to make copies for creating mounts for specific pipe sizes. Leaving it this way makes it more scalable. Delete 90_150. To use the new master revolve frames to create a 1/2-inch PVC pipe mount is very easy. Select 90_600, then click on Edit, Copy, and Paste. Immediately name the new copy 90_151 1/2-inch mount revolve frames. Hide 90_600. Because we used the 1/2-inch mount to create our master, the only thing we need to do is fillet the top of the sleeve profile. Select 90_151. Click on Construct, the Fillet Group button, and the Fillet Verb button. Select the top two corners and enter a value of 1.5. As you can see, it didn't work. Our strategy then is to reduce the size until it does work. In this case, we'll use a value of 1.49. We will now revolve the profile to create the mount. Select the profile and click on Construct Revolve Group and Revolve Verb button. We are asked to pick Revolve Axis Start Point. We will select a point on the Z-axis. The prompt changes to Pick Revolve Axis Endpoint. We'll select the origin and the mount is created. Name the new mount 90_150 1/2-inch mount. And hide 90_151. Each time we create a new mount, we'll need to add the screw holes and apply some fillets. We use center circle to create the first screw hole. We first create a construction line starting at the left side of the top of the flange and moving to the right edge. We use that construction line to center the circle, which is 5 millimeters in diameter.
We are going to use one of the array verbs to replicate the circle. Before using the array verb, it is always a good idea to name the object that is to be replicated so that all the objects can be used or deleted using the object browser. We will simply name our circle X because it's going to be used as a temporary object.
We will now use Transform Circular Array to create 4 new circles. We will use the circles to cut through the holes. We delete the circles and use a chamfer of 2 millimeter to create the inset for the screw head. We go to the 3D view and click twice on the bottom to select the bottom face. We then use chamfer with a value of 1 and click Done to complete the 1/2-inch PVC pipe mount. We'll now demonstrate why this method is called more scalable than the first method. Suppose we wanted to create a mount for a 1 1/4 inch PVC pipe from which we plan to hang fairly heavy stage lighting. This will require a more robust mount. Hide 90-150. Go to the front view. Select 90-600. Click on Edit, Copy, Paste, and immediately name the new copy 90_451 1 1/4 inch PVC mount revolve frames. Hide 90-600. Show 90-400, the 1 1/4 inch PVC pipe. Select Draw Curve, Rect Group 3 points verb button. Use the bottom edge of the PVC pipe to create a rectangle that is the same width as the diameter of the pipe. Hide 9400. Click on the new rectangle and create an outside offset of 0.4 millimeters. Use this offset to align the left side of 9451. Delete the reference rectangles. Show 9400. The mount profiles just don't seem robust enough for the size of this pipe. So we will make some adjustments. Click on 9451 to select the profile and select Edit Show Points. The first thing I think we should do is to make the sleeve longer. Select the top 2 points, click on the Transform tab of Palette 3, and then the Align Verb button, top align. We'll add 20 millimeters to the sleeve length. Click on an empty area to deselect everything. The sleeve profile is just 3 millimeters wide. Since our lights are heavy, we might want the sleeve to be 10 millimeters wide. We'll create a temporary reference rectangle to help us. Draw a curve, rect group, corner, rect verb. Click on the right side of the sleeve profile and make a rectangle that is 7 millimeters wide. Select all of the points that define the right side of 9451. Click on Transform, Align, Left Align, and make sure Move As Group is checked. Align the right side of the sleeve with the right side of the reference rectangle. Delete the reference and turn off Show Points.
Leaving the master sleeve wall with straight corners allows us to choose the best combination of fillet and chamfer for each new size. In this case, we will use the fillet verb for the outside top corner. Click on Construct. Then click on the Fillet Group button and the Fillet Verb button. We can choose any radius between 5 and 1 millimeter. We'll choose 4 millimeters and finalize with Done. For the top inside corner, we'll use chamfer to help us when we insert the pipe into the mount. Select the profile curve and click on the Chamfer Verb button. We'll enter a distance of 2 millimeters and check the Use to Distances checkbox. We use a value of 8 for distance to and click on Done to complete the chamfer.
Hide 90_400 and revolve 90_451. Name the new mount 90_450 1¼ inch mount. This time we'll use more than 4 screws.
We click on Draw Curve, Circle Group, and the Center Circle verb. We will use a construction line to find the midpoint of the width of the mount base and create the circle with a diameter of 5. Again, we will name the first circle before using the circular array. We'll again use X for the name. Click on Transform, Array, Circular. We can try 6. Or even 8. Click on an empty area of the screen to unselect everything. Click on the mount and then click on Construct, Boolean Group, and the Diff Verb button. Select the circles using the Object Browser and click on Done. Then delete the circles using the Object Browser.
Chamfer the screw head offset, a value of 2. And chamfer the bottom face, a value of 1. our new robust mount is complete. The great thing about this second method is that it makes it very easy to widen the flange if we find we need bigger screws, and it will work with any size cylinder. And that's why we call this method more scalable than the first method, where we would have to start from scratch for each size change. We hope this has been helpful. And if you'd like to practice more, well, you can resize for the other pipe sizes. This is 3D Design for Fun and Life. 3D Design courseware based on Moment of Inspiration by Tom Meeks.
In this session, we demonstrated 2 ways of creating a wall mount for PVC pipe to be used to hang a background or lights. This is the 4th of the projects we will include in this course to enhance your life and the lives of those you love. In future projects, we will demonstrate other useful PVC pipe accessories, such as specialty connectors and a wide variety of very useful hangers. Enhancing lives through 3D design and printing is the goal of this course.